Oh, to speak to the, okay, yeah, so you gotta start broadcast to speak to the entire audience.
Okay.
The broadcast is now starting. All attendees are in listen-only mode.
Okay, I think we've got the audio figured out. Would somebody just give me a quick sound check? Can you hear my voice over your computer now? You can either raise your hand and say, I can hear you, John, or just type into the question dialog box. Can you see? I can hear you. Okay, great, great. It looks like we're all set, Kim. Okay, folks, thanks a lot for joining me. Sorry for the small delay here. It's always tricky when you're working with microphones and going through a VoIP ID system on over the internet. But I'm glad all of you could join me tonight for our next webinar science series here at the Weather Service in Burlington. Like the title slide says, I'm John Goff. I'm a lead forecaster here at the office. I've been here about 15 or 16 years, along with a lot of other folks here, and I'm happy to be with you this evening to talk a little bit about the spring runoff and a little bit about the science behind predicting snowmelt, some of the climatology and how we do it here at the Weather Service and predict these sorts of things. So without further ado, I'm going to go ahead and get started and kind of give you a few little ground rules to, as we go forward on how we're going to interact and everything. All right, so before we start, just a few rules of engagement. As many of you have already known, the phones will be muted. It'll just be me talking to you. Now, you do have some question dialog boxes on your screen that you can type a question into. I will try to answer those at the end of the presentation, a few selected questions as time permits. The presentation will be recorded, and we also have a YouTube channel, so we'll put that on our YouTube channel at a later date within the week or two. People can go back and view the recording if you have to check out or do something like that. So those are just a few simple ground rules. I'm not going to be able to talk to you one-on-one. Usually in these type of situations, there's too many people on the line. Just a few rules to understand how we'll do this. But you're always welcome to raise your hand and ask a question, and I'll try to get to it. In terms of an overview of the presentation, a few things we'll talk about. Specifically, I'll go through a few terms that we typically deal with snowmelt, describe those, and help you understand when I talk about those further in the presentation what they mean so you're not confused in that regard. We'll next touch base a little bit on snow climatology, particularly across our region of the world, a little bit about how the snow rises and falls, depths, and things of that matter. Then we'll go on to some basic snowmelt phases. There's 3 primary phases I'll go through on how snow goes through the melting process in the springtime. Then we'll move on to factors that heavily govern the snowmelt. There's a variety of them, but there's some more key important ones that I'll cover here in this presentation about how the snow melts and what makes it melt. Then we'll move on to some measurement techniques that are used to measure the snow and some modeling efforts to predict the snow melt when it is about to occur. We'll also talk about a little bit about forecasting the melt, how we as meteorologists here at the Weather Service and in other science agencies forecast the melting process. Finally, we'll end with a summary of what I talked to you about this evening and then some online resources. I've got about 40 slides here, so I'm figuring about 40 minutes or so, give or take a few. And hopefully this will help you out a little bit, understand a few of the things that govern the snowmelt process and how we go about doing it as we move into the springtime as we are now. So our first term we'll talk about is probably the simplest. It's called snow depth. It's as simple as what it is. It's basically sticking a ruler in the ground, measuring how deep the snow is, record that, that's your snow depth. Typically our observers around here, or when we measure snow depth, we take a variety of readings around a certain protected area of land and then take the average of those measurements. So we may take 4 or 5 measurements, stick it in the ground, get a variety of measurements, take an average, that'll be our snow depth. Because in any given circumstance, the snow may drift or melt or settle around different things, and so you kind of want to get a representative area of how deep the snow is. Very simple. Snow depth is what it is. How much snow is on the ground, how deep it is. The next term I'll talk about here briefly is snow water equivalent. Many of you are familiar with this, but for those who are not, basically what snow water equivalent means, or SWE in the yellow box shown, SWE, is how much water is contained in the snow. So in the diagram I show here, on the left there's a box with 10 inches of snow in it. If you melt that all down to water, it contains 2 inches of liquid water. So when we look at a snowpack, one of the most important things we need to know when it melts and how it's going to affect how rivers rise and etc. is how much water is in that snowpack. Is it a dry, fluffy snow? Is it a dense, wet snow that has a lot of water in it? Typically, snowpacks up here can have several inches of water, if not more, in them, and I'll show you some graphics in a little bit to show you typically what we look at and how much it's usually across our mountains and valleys in the winter. So again, snow water equivalent, or SWE, how much water is in the pack. Our final term I'll talk about here before we move on is called snowpack ripeness. This is a little bit more difficult to understand, but not really too bad. I've got a graphic here with a yellow box basically describing what it means. It's basically indicative of how close is the pack uniformly close to 32 degrees Fahrenheit or melting, i.e. near full melt. So if you look at the chart here to basically describe it, you've got the ground surface at the bottom in gray. You've got a depth of snow going up the axis in the middle with the hatched tick marks, which is about, in this case, about 150 centimeters deep. And then the blue area at the top of the chart is the free air. So in any given day, looking at the blue line, the snowpack temperature will be coldest usually at the top in a midwinter, and then warm slowly kind of close to freezing when you get all the way down to the ground, because the ground typically, if you get snow early, is going to be kind of a uniform temperature. So this is a very typical temperature profile. And then if you noticed on the very top part of the blue line, that very top 10 to 20 centimeters will change temperature daily as the temperature rises and falls. So in the evening and night, it's the coldest, shown by the arrow. It may fall very cold, and in the daytime, the top few inches will warm as the daytime warms. Now, when you get to snowpack ripeness, what happens is you have enough warmth in the early springtime or late winter that the entire snowpack temperature curve shifts toward freezing, and that's denoted by the red line. I kind of drew my own little line in there for you to show you how it may be actually a little bit above freezing in the daytime, maybe 2, 3, 4 Celsius, then cooling down to freezing and slightly below as you go down through the snowpack. That's what we mean by snowpack ripeness. Slowly warming of the snowpack close to 32 Fahrenheit before the melt. So let's move on to a little bit about climatology and annual snowfall climatology, especially across our region of the world. This certainly varies across different continents and different parts of the United States and Canada. Typically in our region, on a given year, the broader valleys will pick up anywhere between 60 and 80 inches of snow. The mountains somewhere between 80 and 130 inches, and what I mean by mountains is in the northern mountains where people live. And then as you get higher up, above 2,000 feet, and all the way up to the summit level, you're talking annual snowfall averages anywhere between 150 all the way up to as much as 250 inches, or even sometimes higher in a big snow year. Now, I will say on that bottom bullet, which is very true, a lot of intra-seasonal variability. Some years you can have big snow years. Some years, like this snow year, it's been a pretty average snow year. Very cold, of course, but not a lot of big nor'easters. Those were affecting a lot of southern New England. So we've had a pretty average snow year this year. A lot of seasonal variability from year to year with the snowpack. I always like to use this graph in terms of the greatest average snow depth. This is from the UVM Burlington Eco-Info project, and it's basically a graph that shows the multi-year average of accumulated snow depth on the summit of Mount Mansfield in northern Vermont over the last 60 years. It's a great long-running climatology. The green bar shows the average 50-year, 60-year climatology for snow, and basically it shows how the snow slowly starts to increase by late October and early November, indicated by the dates on the bottom of the graph, and increases and maximizes sometime in the middle to later end of March at the summits. You have a little bit of a dip, it rises a little bit in late March, early April, and then it really falls off the table when you get from about the second week of April on. The very, very typical type of climatology, even on a a high snow year or a low snow year. These are very dependable averages, and we look for the summit peak snow depths to occur, again, in late winter, mid-March, late March type of time frame. Rapid melt begins in April. Let's look at a couple other sites outside of the summit levels, actually down where people live. These are box and whisker plots, basically probabilistic charts, so to speak, that show, statistical charts, I should say, that show the average snow depth per month in Burlington, Vermont, which is denoted by the easternmost red star on the little green map in the chart. And the blue boxes basically show the 25th and 75th percentiles, high and low, of what you would expect for snow depth in each month. The black bars within those blue boxes are the median values. And then outlying the black boxes are the 10th and 90th percentiles with the maximum values denoted by the little x's. Some of the months, the actual maximum values are actually pretty high, and I can show you right up here on this line. Let's see if I can get my pen here. This little line right here, these are all actually the maximum values for the month. So 33 inches, 40 inches, 33 inches, 31 inches for the month. But basically what it shows in the valleys is that the actual snow depth peaks in late February to the middle of March, actually a little bit before those summit snow depths that we saw in the earlier graph. So the valleys tend to have a maximum a little bit early, 2 to 3 weeks earlier than the summits. This is another site, Tupper Lake, New York, about middle elevation, 1,000 feet. Very typical climatology for a mid-level elevation. You'll notice that the snow totals and median values for snow depth are higher. Of course, it's higher up in elevation. It's going to be colder and gets more snow. But the main idea is still the same, that you're basically looking at late February into early March before it starts to turn the corner and rapidly decrease. Again, so a few weeks earlier than the summit level. I kind of want to just make that distinction. And that's pretty much the case this year. If you're in the Champlain Valley this year, you can notice that most of the snow is gone already, while if you get out of the valley, there's still quite a bit of snow in the hills and mountains. Now let's move on to another topic on our list tonight to talk about, basic snowmelt phases. There are 3 of them. There's a warming phase, ripening phase, and output phase, and I'll discuss all 3 of those. The warming phase is pretty much what it describes. The absorbed energy raises the average snowpack temperature to a point at which the snowpack is nearly isothermal, near 32, no temperature gradient. Okay, so it's kind of like that ripening phase, but it's actually just the snowpack process warming and raising in temperature. This is when those graphs start tumbling off the edge, when you start losing your snow depth. The snow is warming, it's getting more dense, and it's compacting. And I'll illustrate this to you in a little bit on some other data. So first phase, warming phase. Then we move on to the ripening phase. So what happens in the ripening phase is the absorbed energy is used to melt snow, but the meltwater is retained in the snowpack between the pore spaces of the snow grains by surface tension forces. So at the end of this phase, the snowpack can't retain any more liquid water and is said to be ripe. So if you look at the graphic here, you have the snow grains denoted by these gray little balls here, and then the water is melting, but it stays trapped between the snow grains. So the snowpack still holds on to most of the water. There's even some air in here. It holds on to most of that water, and basically the snowpack starts to get more dense and compact. And it typically happens again in this ripening phase during the late winter, early spring. So you'll notice the snowpack gets thicker, harder, denser. That's that whole phase of compacting, and there's a lot of water can be trapped up in that snow. It's not really releasing a lot of the water yet. And then finally we move to the output phase. Further absorption of energy produces water output, which then appears as runoff, melting water into the streams and lakes and rivers. Infiltration, which is basically just a fancy term for it soaks into the ground. Or evaporation, the water runs out across the surface of the snowpack. It's a windy day, it evaporates. The 3 main ways that the water is removed from the snowpack. So again, remember, warming phase, ripening phase, output phase. Those are the 3 main phases of how the snow basically melts and goes away. This is kind of a little graph I kind of jimmied up just to try to give you an illustration of that, showing on the bottom November through April during a cold season. The blue line showing the snow depth varying but slowly increasing through time. And then once we reach the warming and ripening and output phase, a sharp decrease in the snow depth. It's compacting as well. So if you look at the green line, which indicates snow density, how dense the snow is, that's slowly increasing over the entire winter and begins to tick up fairly sharply right at the end of the melt period. Because if you can imagine, as the snow gets completely ripe and starts to lose its water, it's got just a ton of water in there, so it's very dense and heavy. So again, the melt period right at the end showing how the snow depth decreases rapidly and the snow density starts to take a strong uptick. Now let's discuss some factors governing snowmelt. There's quite a myriad of them. There's some that have more importance than others depending on the time of year and what's happening. I certainly can't go through all of them. Some of them are quite complex that deal with surface radiation budgets and more scientific terms. But I'm going to go through the main 5 that we typically like to talk about here and what factors we look at. And they are solar radiation, the heat transfer process, effective slope angle, ground temperature, and then other factors such as turbulent mixing, forest canopy percentage, such as how much shade is over the ground or how much sun is reaching the ground, things of that nature. So in terms of solar radiation, I always like to use this graph. It's lowest in the winter, of course, right? The sun angle's low. Highest in the summer, the sun angle's the highest. And the stronger solar radiation in the spring helps to warm the snowpack toward ripeness. It's not necessarily the biggest factor on any given day, but it is one of the more major factors. If you look at the chart, basically running from January to March and through the summer, you can highlight these curves. Basically on the y-axis it discusses how many millijoules per meter squared per day you're getting of solar radiation. And I've highlighted the red curve, which is 40 degrees north latitude, a little bit further south than us, but close enough, and showing how the curve maximizes in the summer, is minimized in the winter. Okay? If you look at the January total radiation budget versus the March radiation budget, you go from about 15 to almost 30. So you're almost doubling the solar radiation just from January to March. And by the time you get to May and June, you're like tripling to quadrupling it. So it's a law of increasing returns on how much solar radiation is hitting any square patch of land. And you can look at the other curves there. 40 degrees south would be the exact opposite of us. And interestingly, this is not really related to our topic, but if you look at the equator line, which is the darker, thicker line, you'll notice that in the middle of summer we get more solar radiation than the equator does. And that mainly is due to longer daylight length, not as much sun angle. The solar radiation at the equator, it's always about 12-hour days, 12-hour nights. But in the middle of summer, we actually get more solar radiation than the per square patch of land than the equator does, just because our days are so long. Another big factor governing snowmelt is the heat transfer process. We like to think of this as called latent heat transfer. It's a fancy term of just heat being transferred from one object to another under a constant temperature regime. Warmer air flowing over colder snowpack condenses on the snowpack. That is a latent heat transfer process. If you think about evaporation when you get out of the shower or you get out of the water from swimming and the wind's blowing on you and the water's evaporating off your body, it's a cooling process. The exact opposite happens when you condense water. When you condense water, it releases heat. So warm, moist air above freezing air over a snowpack, it creates fog, it condenses water droplets and moisture onto the snowpack and releases heat into the snowpack. Big input of heat into the snowpack. It's a warming process. Big factor, especially on a real warm night. If you still have a lot of snowpack and it's 55 degrees and your surface dew point's in the 40s, can really add a lot of heat to the snowpack and help bring that snowpack toward ripeness. And this is just another idea or another process by which heat is transferred to the pack. Warm rain falling onto a colder snowpack also releases heat. So if you think of 10 degrees Celsius rain, which is about 50 degrees Fahrenheit, falling into the snowpack, it's not ripe yet, so it just gets absorbed into the snowpack, but all that warm rain releases heat into the snow. The raindrops cool, the snowpack warms, they reach some sort of equilibrium. Heat is released into the snowpack, helps raise the temperatures. So big warm rain. We've had some events in the distant past, and I'll cover one later in the presentation. You know, thunderstorms falling on the snow, bad things happen because it can melt a really lot of snow because your rain is very warm. This is another really big one, effective slope angle. South-facing slopes, we all know that generally, they melt faster than north-facing slopes due to the instant solar angle and the greater shortwave radiation per square meter or square patch of land. So in the diagram shown here, south-facing hills with a south aspect facing the sun, the snow melts a lot faster than those north-facing slopes where the sun angle is much more shallower. This also has to do a lot with forest canopy. You may know or may be familiar, a lot of conifer trees grow on the northern sides and the cooler, moisture sides of the mountains, and the conifer trees have their needles all the way through the winter and spring, so there's a shading process on the north side due to the forest canopy as well as just the sun angle. So a big deal on the sun angle, especially as you move through spring. And then finally, we'll also talk about, or at least another one, about ground temperature. The ground typically provides at least some minor upward heat flux or heat transfer up into the bottom of the snowpack through conduction. Conduction meaning it's touching the snowpack and it transfers the heat from one body to the next. In this case, the ground or soil into the bottom of the snowpack. This is typically a little bit more minor of a deal, but it can be more important in late spring if you get a snowfall, or early in the season. If you get an early season snowfall in September, early October, or you get a really late snowfall, late April, early May, the ground by that point is already warmed up a lot, and it'll tend to start melting the snow from below just because it's already above freezing. If you get a real cold snap before you get a lot of snow in the late fall and early winter, the frost depth can be pretty deep and the ground is frozen, then that effect can be minimized because your ground's already frozen. So those can be variable factors that happen in terms of ground temperature. But typically, other than in the very early part of the season and the late part of the season, the ground temperature influence is not quite as much as these other factors. Okay, now let's go ahead and move on to some techniques, how we measure the snow, and a little bit about modeling. In terms of measuring the snow, we have field observations, like direct observations, shown like the guy in the picture here. We also have remote sensing observations taken by equipment, and I'll go over both of those. Again, we'll talk a little bit about modeling toward the end of this section, not going too in-depth because it's a heavily a heavy science-based type of thing, and I don't want to confuse anybody. In terms of field observations, your manual measurements come from us, me, the meteorologist, our NWS cooperative observers, which are a number of volunteer observers that are around New York and northern Vermont and central Vermont that actually daily go out and measure the snow in that SWE, that snow liquid water equivalent for us. And then we also have something called Hydrographs volunteers, and this is another precipitation measuring network that's free. There's a web face that you can go in and enter your snow depth and your rainfall. I've got some web links at the end of the presentation to show you if you care to write down some of the stuff here I've talked about, including the Hydrographs link, if you're interested in doing that. There's a use of snow tubes and calibrated scales. There's some hiking involved when you do these manual measurements, shown by the two fellows here. We'd all tend to try to pitch in here and go out and take our hikes in the woods. We have some designated spots that we go through across the North Country. We take snow cores in these hollow tubes. We have a scale that's calibrated. We weigh it, get a snow water equivalent, we get a snow depth, and we go back and enter the data, and it helps the modeling efforts. Usually snow depth and snow water equivalent, those are the main things we would be measuring. Field observations, now these come, and I'm talking about more like automated or remote observations. They can come from a variety of different sources. Generally, again, talking about automation here. Not really particularly focusing on any of the graphs or the dots here, but just the main idea is there's a couple ways to do it. SNOTEL sites is one of them. This is the National Resources Conservation Service. They're very heavily vested in the western United States by placing a lot of these automated snow measurement sites out in the Rocky Mountains and the Sierra Nevada. Very important for water resource management issues out there, how to measure the snowpack, how much available water is going to be coming down the rivers into the spring and early summer. And even more vital so now, as much as we talk about this, a big long-term drought developing out west in California in the west, a lot of really dry areas out there, and they haven't had a lot of rain out there. So these type of measurements are very, very critical. SNOTEL sites, again, the National Resource Conservation sites, and they use something called snow pillows. It's kind of shown on the far right picture here. There's kind of, and I'll try to draw it if you can see, they kind of have this flat kind of plate that kind of sitting on top of the ground, and the snow falls on that, and it can measure based off of certain telemetry how much snow is on the ground and the snow water equivalent based off of what's fallen. Automated sites, and then there's different plots of the data you can look at based off the site to see, and I've just kind of given you a picture of one here, a little graph that shows, I believe that shows snow depth on one of these sites. Again, automated sites, mainly out west. I believe there is a SnowTel site on the summit of Mount Mansfield, just below the summit level, but I don't think we have access to the data, and I'm not positive per se if that's even operational right now. But it's the same type of thing that they do out west. Most of them are out west, though. We also have airborne surveys, pretty interesting stuff. The National Operational Hydrologic Remote Sensing Center, or what we call No-Risk Center in Minneapolis, is our national, basically NOAA, National Weather Service snow gurus that take all the measurements and do a lot of modeling efforts and show us the characteristics of the snowpack across the country. They fly aircraft as we get into the deeper winter, and especially as we move in towards spring. And they fly flight lines of about 1,000 feet wide and 10 nautical miles long. So it has a footprint of these surveys of about 2 square miles. And they fly really low. They only fly about 500 feet off the ground. And they use gamma radiation pulses from an instrument in the bottom of the aircraft to measure the snow water equivalent SWE. And they can also measure soil moisture and a few other type of parameters that we look at. The data is then shared with the National Weather Service offices and also the regional river forecast centers that we coordinate with to forecast river flows. Very important data. Again, mid to late winter, and especially as we move toward the spring melt. And this is just a plot from that NORIS site of some of the flight lines that they flew back in late January and early February across northern New England and into New York. And the green little swaths showed the swaths that they had completed by that date, and the red swaths, little tick marks, show the flight lines that they had yet to get to, at least in this 1 week period in late January and early February. About 70% complete. And they do these several times through the course of the late winter to measure the snow and SWE and give feedback and input into the models, into the forecasters. Another category of remote sensing, satellite data, of course, can be very important. It's obtained from geostationary and polar orbiting satellites. Geostationary meaning a satellite that's just fixed over one point of the Earth. Polar orbiting satellites meaning satellites that fly in low Earth orbit about 500 miles over the top of the Earth and spin around the Earth several times a day, north to south. 2 different types of satellites. And the data is also incorporated into forecasts and modeling efforts. As you can see on the chart here, this is just a sample chart from March 20th, a few weeks back, showing basically most of the snow cover was gone, except for the northeastern part of the country. Lucky or poo-poo to us for either having it, depending if you're a snow lover, if you're not. And again, some snow across the Rockies, but most of the country, at least a couple weeks ago, was already void of snow. Okay, let's talk a little bit about modeling efforts. That NORIS, that National Operational Hydrological Remote Sensing Center, and the River Forecast Centers also model the evolution of the snowpack through the winter. There's a lot of inputs. I just kind of have a chart here. I'm not going to go over that chart. It's just I kind of wanted to give you the idea. There's a lot of factors that go into a physical model of trying to predict snowmelt. Okay, and these people are the experts that deal with this thing. I actually don't deal with the physical model myself on a daily basis. I see the model output and then provide input back to them to tell them, does it look good? Does it have a high or low bias? Is it fairly accurate from what I can tell? That's kind of my job, and then forecasting the melt. These guys are the scientists that actually develop the models. There's a lot of empirical and physical inputs into the systems. Snow 17 and SNODAS are probably the 2 primary models used by the River Forecast Center, which in this case I listed NERFC. That's the Northeast River Forecast Center down in Boston, which is who we collaborate with for New England and Northern New York. But there are several other ones around the country, and then that NORISK Center. So if you query on Google Snow 17 or SNODAS snow model, you can probably go as deep as you want into understanding how those models are developed and what they do. But again, very important modeling efforts, because you need to kind of know what the model's predicting. So these are just some sample charts that are produced by that NORISK National Center. And these are snow water equivalent graphs. I just kind of popped these on a couple weeks ago, March 21st, I think. So the larger picture in the upper right shows the snow water equivalent across the country, and it's color shaded, and you have a color bar on the bottom, and shows what the modeling and remote sensing data show how much water's in the pack. And it also incorporates those manual measurements I talked about, where the people are going out in the field, or the observers that are measuring at their homes every day. That data gets sucked in to the modeling efforts as well. I failed to mention that earlier. So you get these nice pretty charts, and then you can compare them with reality. It's not always perfect. A model is a model. It is what it is. Sometimes it can be good, and you can really rely on it heavily. Other times you can say that's garbage. It doesn't look real at all. In the lower left-hand chart, you can have some zoom capability function, and this is the type of stuff that I would look at as a meteorologist. I'm not looking at the whole 48 states in general, because I'm just forecasting for our particular area. And then I would look at the charts here, and I can play around with certain types of parameters of the snowpack to see how it's behaving as we move toward the melt. This is another example of one of those charts. This is snowpack temperature. Don't worry about all the little words on the left-hand part of the web design, of the web page there. All I wanted to show you here is this is kind of a little graphic they produced that we look at, and you can get it yourself. Once I'll show you the link at the end of the presentation, you can access all this data. You have to play around with some stuff on the left. This shows snowpack temperature, so all the red colors is where the snowpack is near about 32 degrees Fahrenheit, shown by the legend on the right, so that's near ripe. That would be snow that's near ripe, and if you know the Champlain Valley, we've lost all our snow. So as of about 2 weeks ago, what we had left was basically ready to melt away. And you can see colder snowpack temperatures in the mountains where it's not ripe yet. And these are, again, some types of the charts we tend to look at to get a gauge on the behavior of the snowpack and what it's doing. Okay, let's talk about forecasting the melt as we get toward the back third of the presentation here. We have some general rules we like to talk about just as forecasters that we think about. They're pretty empirical rules that we use to look at stuff. And then also we'll talk about the hydrologic response, typical river responses when you see snow melting into the rivers. So some general rules of thumb. The snowpack must be near or fully ripe for the snow to melt, right? If it's not ripe and the whole snowpack temperature, remember some of those graphs I showed you earlier, if the snowpack temperature as a whole is 24 degrees, it's not going to melt. So you need a fully ripe snowpack getting ready to go into that output phase I talked about. You need persistent above freezing temperatures. Of course, increasing sun angle helps to ripen the snow, late in the winter, but you can have a thaw. We had our thaw generally this year in early January, and then that was it. Late December around Christmas time. Actually, the thaw came a little early this year. So you can have above freezing temperatures and get that snow to melt early in a thaw. Also, warm rain and mild moist air on snowpack. We talk about this latent heat transferring of warmth to the snowpack through those processes. So when we see a warm air mass coming in, 50s and very moist air, we start thinking melting snowpack. Okay? Certain types of events will do it more than other depending on how mild and moist and how much rain is falling. But very important to watch for those type of situations. And we're coming up in the next couple of weeks where we're going to start encountering some of those situations where the snow is going to start going away pretty rapidly. The flooding threat from snowmelt usually is minimal unless heavier rain occurs on a ripe snowpack. Most years we don't get a ton of bad flooding. If everything plays out the way it is, April tends to hopefully dry out and behave normally. The snowpack slowly goes away. We may get a little minor flooding here and there. Then after that, it kind of just goes away and the rivers recede. Now, last year we did have some pretty decent flooding. We did have an event through the middle part of April. We had some ice jamming and some flooding. Not terrible, but a few places were hit pretty hard. A lot of other years, not as bad. I think I remember a winter back in 2001, 2002, or one of the early 2000 years where we had a huge snowpack. Some of you folks may remember that were here at the time. We had a couple big nor'easters, a lot of snow in about the middle of March. We were really worried about flooding, and April turned out to be very warm and dry, and it just went away, and nothing happened. So a lot of these factors have to kind of come together to really produce a big flooding scenario. So that's the good thing. The flooding threat is usually pretty minimal. And this is a typical hydrologic response to snowmelt. The peak melt typically occurs during the daylight hours, and it can vary depending on the river because it can be a lagged response to the river stream gauges by several hours. We see these curves based off of what the river gauges tell us and based off of the input from other streams and rivers upstream of those gauges. So depending on how fast the rivers flow, how fast the runoff is, you typically see the peak runoff occurring during the daylight and early evening hours, and then the time-lagged response occurring a little bit after that, depending on the watershed. But one of the most, I guess, the one thing I wanted to show you too on this chart is that a very typical hydrograph response to snowmelt is this sinusoidal pattern, and you can kind of see the daily ups and downs and response of the river as it goes through the melting and then the cooling down as you go through March and April. You can see a rainfall event in there, at least on this graph. This is just a graph from Japan. It doesn't have anything to do with us, but it clearly illustrates the up and down sine wave pattern that typically occurs during the spring melt. Now, if you have rain on top of that, sometimes the curve can go up. So sometimes, and if hopefully you can see my drawing, sometimes it'll do one of these deals. It'll go up and up and up, and that's where you got to kind of be careful and watch those hydrographs. A lot of times you'll be getting rain during those events, and you'll see that sine wave pattern embedded within a gradual rise in the river, and you have to pay attention to those carefully. But when you see that kind of up and down pattern, very, very typical of a snowmelt. So here's one particular event I mentioned earlier about thunderstorms on snow. I think some of you will remember this. Late April 2011, thunderstorms and melting snow. Very bad combination. Federally declared disaster for several counties, especially in the Lamoille River Basin. Damages were about $9 million. So again, at this point it was late April, so most of the valleys had cleared out of the snow, but we still had a lot of snow above about 2,000 feet. And you had heavy thunderstorms with a lot of rain falling on melting snow. So summary of that event, 1 to 2 inches of liquid rainfall, and then you lost about 1 to 3 inches of a higher elevation snow melt. And that little graph up top kind of shows how much snow was lost during that event. So if you can see like the Adirondacks here, I mean they lost, some of the high peaks lost 3 inches of snow, 3 inches of sweet out of the snow. It all went away, basically in one night, which is what you don't want to have happen. You want to kind of gradually melt it away. So major flooding on several rivers. This was Cambridge, Vermont in the lower picture. So some high impact, especially along the Lamoille River. I believe the Ausable had some pretty good impacts as well on this event. So when you see an event like that, you got to be very careful because you're weighing in all those factors. Warm rain, latent heat condensation, the snowpack was ripe, warm moist air, all those kind of things come together. Luckily, it doesn't happen that often. So in summary, as I wrap up here the last few slides, the climatology shows that the spring melt typically occurs generally late March, but most particularly in April. The snow melt process has 3 distinct phases. If you remember that warming phase, when the snowpack temperature rises, the ripening phase, where the snowpack condenses and the water gets trapped in the snow pores, and so it's condensing and a lot of water is trapped in there, but it's not releasing the water yet. And then the output phase, again, when the water releases out of the pack. The snow melt occurs to a combination of various factors. We talked about sun angle, latent heat transfer, all sorts of factors that involve conduction through the ground, things like that. Observations of the snowpack can come in manual form, going out there and physically hiking through the snow and measuring it, automated and remotely sensed data sets. So the automated, things like the SNOTEL sites out west and those snow pillows, remotely sensed data sets from satellite and modeling efforts and the gamma flight survey lines from the aircraft. Modeling of the snowpack by regional and national centers are vital in coordinating timing and strength of the spring melt. Very important as we look forward into the spring melt, how this thing's going to play out. And a lot of factors go into those models. Very complex physical models, but fairly easily to understand output. When you look at the websites and some of the graphical output, a lot of the simpler things can be understood really pretty straightforward. And there's several rules of thumb that we use as forecasters to predict the timing and magnitude of the melt, and I covered a number of those. The hydrologic response to the melt is noticeable, but typically the flooding is minor. As I showed earlier on that hydrograph response, a typical sine wave pattern, the ebb and flow of the melt during a daily basis, usually time lagged by a few hours on those hydrograph responses. But the good news is most years we don't get a lot of major flooding. So I'm going to leave it on this slide just for a little bit because this is basically my last slide. If anybody is interested in our box and whisker snowfall climatology, Peter Banakis, one of our lead forecasters here, has done a lot of great work in developing snow climatology for a number of sites across our particular area. So that first website there will take you to some box and whisker data of sites across our area. There's some really good educational materials that are more in depth than what I covered here that I could cover in 40 minutes on the Common UCAR educational module on snowmelt processes. It's free. You have to sign up and create a password, but it covers a ton of meteorological modules on a variety of topics, anything from fire weather to thunderstorms, and in this case snowmelt. So that link there will take you to the snowmelt module, and it's pretty in depth, but it's easily understandable. If you want to know more, you can go through that. The National Operational Hydrological Remote Sensing Center page, the one that models and gives a lot of those graphics, or is at the third website there at norisk.noaa.gov. Northeast River Forecast Center in Boston does some snow modeling information. We work closely with them on their local river flows. There's their website. We also have a write-up from our local office of that April 26, 27, 2011 event that goes into more detail of some of the hydrologic responses and the meteorology behind what happened during that event. So there's a link to that there. And then finally, if you're interested in measuring rain and snow forests for the National Weather Service, the Community Collaborative Rain, Hail, and Snow Network, or COCOROS, has their homepage at cocoros.org. It's a free network. Basically, you have to spend about $5 or $10, or maybe a tiny bit more, get yourself a proper rain gauge, and then you create an ID and go to a free website and you just enter your data. You can measure it every day if you're really into it, or just measure it when you're home, when you can do it. And that data we suck in to our system here, so we'll get your snow data, we'll get your precipitation data, that kind of thing. It's mainly a precipitation data network. So if you're interested, you can go to that cocoros.org website. And finally, for some reference information, just like we did with our first website, the river ice processes, the recording that I've shared with you tonight will be available on our YouTube channel at youtube.com user NWS Burlington. That'll be posted in the coming weeks, and we'll be working on that also to get that closed captioned for you for those that are hearing impaired. And you'll be able to review that if you want to go back over some stuff that I covered tonight, or have somebody else, a friend or family member, listen to it. And if you have any questions about any of the topics I covered tonight, send an email to er-btv.socialnetwork@noaa.gov, and we'll be sure to get back to you. It's probably going to be me, but it could be somebody else in the office. So that's all I've got to share with you tonight. Let me, I'm going to bring it back to the screen, and if anybody has any questions, briefly, I can try to answer any of those. Let's see if anybody's got any. Okay, this is from Bob Dill. In the spring, how does snowpack get above 32 degrees without melting? When will the frost in the ground melt? How deep has it gotten through this winter? Those are some very good, well, okay, I'm not sure, that may be from Carter McKay, I'm not sure. But for Bob's first question, when it gets to 32, that's a very good question. It does melt a little bit on top, but it more just compacts. The snow crystals break down into more of a granular form, Bob, and it tends just to compact and melt, and the water kind of goes within the snowpack. So that I probably should correct myself. I mean, the snow does not release its water, but it's melting and compacting a little bit. And the snow grain crystals are changing and metamorphosizing into kind of more of a, not snowflakes anymore, like granular type of material. And you've kind of, most of you have seen what old snow looks like. It's not snowflakes anymore. It's turning into kind of an icy material. That's kind of his. But the main point I guess I wanted to get home is when you get that ripening phase, it doesn't really release its water. It can just kind of, it condenses down and metamorphosizes. In terms of, let's see, what other question? When will the frost in the ground melt? How deep has it gotten through this winter? I think that's from Carter McKay. I'm not sure. It kind of crosses over from two people. Carter, very good question. It's gotten fairly deep, but in some parts of the state it's not. Typically what we see in the mountains is the frost depth never gets nearly as deep as it does in the valleys, and that may seem counterintuitive, but the main deal there is it snows earlier in the mountains, and they get a snowpack built up so quickly in the early part of the winter that the ground really doesn't have a chance to freeze really deep, and then through the conduction process of those warmer ground temperatures underneath, the ground stays fairly near 32 or slightly thawed. However, what happens in the valleys, we don't get enough snow too quick, but it gets cold, and your frost depths can go deep. So the frost depths this year have ranged anywhere between about 18 inches and 30 inches deep across the state. It's now beginning to thaw. We did a frost measurement here today at the airport in Burlington. It was basically completely thawed after we warmed up this morning, down to about 6 inches, and then it was frozen from 6 inches down to 19 inches, and then beneath that it's not frozen. So that's kind of melting and coming down, and the frost is slowly coming out of the ground. Let's see. Yeah, the frost depth is more deep, but we have colder days with snow cover. Correct, Carter. Abby Fox, any words of wisdom for those poor Californians today of all days? Yes, I saw that executive order on that news release, Abby, from Governor Brown's office in California about mandatory water restrictions out in California. Major deal going on out west, and it's going to be becoming more and more grabbing the news headlines over the coming summer because they basically got no rain out there in the west this winter. Very minimal. The Sierra Nevada snowpack is running anywhere between about 15 to 20% of normal. It's very low. So big time water problems ongoing out there. And I was looking at some data earlier from Alaska just in this past March, and it was just crazy how warm Alaska's been. Most of the month, Fairbanks, Alaska, up by the Arctic Circle, half the month had highs from 35 to 50. So they were for the most month much warmer than we were. So just some crazy weather patterns. Let's see, another one from Carter McKay. Does all of the frost that is in the ground directly go into the groundwater? Is it visible at all to a view on the surface? That's a little bit hard on the frost. It's a very minor contribution to groundwater, just a little bit. Most of your water output that comes into the rivers and streams in the winter and spring is going to come through the snowmelt. Some will percolate down early in the winter and absorb into the ground, but usually we're freezing up pretty quick, so there's not a ton of release from the ground. There's always some contribution, but it's not as major as the snowmelt as a whole. Okay, well I think that's about it. Hopefully I answered a few of the questions there that helped you out there. Again, send an email to that social network email there. If you have any other questions, I'll be sure to get back with you in the coming week if there's something I didn't cover tonight. But again, I want to thank you all for joining us tonight, and look forward on our webpage or through social media for upcoming webinars. I know for sure that we've got another webinar coming up, I believe in late April or early May, that's going to concern the development of thunderstorms and the thunderstorm life cycle. So as we move into the spring and summer, we're going to start moving out of these winter themes and moving towards summer and spring themes that deal with summer weather, flash flooding, thunderstorms, lightning, things of that nature. So hopefully that may interest some of you as well. Again, thanks a lot. Thanks for joining us tonight, and have a nice evening.